All right, welcome everyone. Today, we're going to be looking at how to convert between polar and Cartesian coordinates. So last time we introduced the polar coordinate system, saw how to plot points there. Today, we're going to see how to convert back and forth between polar and Cartesian, our normal rectangular x and y coordinates. And we have a few formulas, a few equations that we use to help us with these conversions. So let's say we know our polar coordinate, we have our polar coordinate point, and we want to convert it into Cartesian coordinates. Well, that means we know r, we have a theta value, and we need to find x and y. So the two equations we use, and it's really nice, we have this equation that tells us exactly what x is. X is equal to r times cosine theta. And for y, same thing. We have this nice equation that tells us what y is. So y is equal to r times sine theta. So going from polar coordinates to Cartesian coordinates is just a matter of plugging in, evaluating, and then you're done. You have x and y. So this one's actually not too bad. Going from Cartesian to polar coordinates sometimes takes a little bit more work. So in this case, we know x and y, and we need to find r and theta. And so the equations that we use in this case a lot of the time are, well, r squared is equal to x squared plus y squared, and tangent theta is equal to y over x. So you can see there's a little bit more work here in finding r and theta from these two equations. We don't have an explicit formula like we do for the first one here, polar to Cartesian, that tells us x is equal to this, y is equal to this. Here there's a little bit more subtlety. We have to actually do a little bit more work here. All right. So before we get into some examples of how to do this, let's see where these equations come from. And let's draw a little example, and they're going to come from right triangles. All right, so let's say let's draw our coordinate system. Let's draw it in Cartesian coordinates first. So x and y. And here's our origin. And let's say we have some point P out here. Now, we can think of this point P as being represented in either polar coordinates or Cartesian coordinates. So let's draw in what both of those representations kind of mean. So if we think in Cartesian coordinates, we can think of this point as x comma y. And so what x and y measure, x measures the kind of the horizontal distance here, and then y measures the vertical distance. So that's what rectangular coordinates represent. X gives us the horizontal distance from the origin to point P, and then y gives us the vertical distance, technically directed distance. So there's some direction here, but in this case, y is just the distance from point P down to the x-axis. All right, so that's if we're thinking of point P in terms of rectangular or Cartesian coordinates, but we could also think of it in terms of polar coordinates. So what do polar coordinates measure? Well, here we could think of it as r comma theta. R represents the distance from point P to the origin, so it's the length of this side. And theta gives us the angle measurement from that line connecting the origin and point P with our polar axis, which is normally the positive x-axis right here. So r gives us the distance, theta gives us the angle value if we're thinking in terms of polar coordinates, x gives us this horizontal distance, y gives us this vertical distance if we're thinking in terms of Cartesian, and what we've just drawn here is a right triangle. So we know that trig functions are somehow involved with these right triangles. And we've looked at this before, but let's review it again. We know cosine of theta is equal to the adjacent side of that triangle over the hypotenuse. And so what's the adjacent side? Well, that's x, adjacent to angle theta. It's x. And the hypotenuse is r. So we get x over r. And if you solve this equation, cosine theta is equal to x over r, you get this first formula. X is equal to r times cosine theta. If we do one for sine, sine is the opposite side over the hypotenuse. So the opposite side is the side of this right triangle opposite angle theta, so that would be y, and the hypotenuse is still r. So this would be y over r. And if you solve this equation, sine theta is equal to y times r, well, you get this other one. Y is equal to r times sine theta. So really, these equations are just coming from the fact that we have this right triangle here. Now, what about over here with r squared is equal to x squared plus y squared? Well, that's just the Pythagorean theorem. So we know the sides of a right triangle are related. So that other equation, r squared equal to x squared plus y squared, is really coming from the Pythagorean theorem. The length of the hypotenuse squared is equal to the sum of the other sides, each squared. All right, so what about this tangent theta? Well, we also know tangent theta. We have a formula for that in terms of the sides of a triangle. So it's the opposite over the adjacent, which in this case is just be y over x. All right. So really, these different formula that we have here really just come from identifying that this is a right triangle and then just using what we know about cosine, sine, and tangent and the Pythagorean theorem. All right. Now, we're going to be, if we look at this, a lot of what we're going to be doing is evaluating trig functions at specific theta values. So we're going to need to know, some values for cosine, sine, and tangent in order to help us with this kind of converting back and forth. So let's review some of the trigonometric values at the important angles. These are the angles that we're using most often. And, here we have our portion of our unit circle. And this is the portion that's in the first quadrant. And it really is important to know the values for these theta values, or the trig values that occur at these thetas in the first quadrant, because then we can use those to figure out the trig values in all of the other for all of the other theta values. So if we know the trig values for the thetas that occur in the first quadrant, we can figure out the rest. So let's kind of review this. I'd expect you probably have seen this before, but it doesn't hurt to review this. So let's first look at the important angles. So what are they? We talked about this last time. So we have theta equal to 0. That's the kind of the positive x-axis here. Then we had pi over 6. Then we had pi over 4. Then we had pi over 3. And then here we had pi over 2. So really, these are the kind of the 5 important angles that we should have, the values we should have memorized. And then we can use these values to figure out, fill in the rest of the circle, essentially. All right, so this is the unit circle. So that's a key thing to note here. This is the unit circle. And what we mean by the unit circle, it's the circle with radius 1. All right. So we want to know the coordinates of each of these points, essentially. And the coordinates of our points would give us x, would give us cosine and sine. All right, so let's look at this first point here that occurs on the unit circle on the ray theta equal to 0. So what would be the coordinates of this point? Well, we're going to write it kind of in a very unsimplified way. And I think it helps to doing that kind of helps to with the other ones. So we're going to write this as square root 4 over 2, comma, square root 0 over 2. So you can tell, not very simplified there. And what we're going to do to get the rest of the values is we're going to just work our way down with that number inside the square root for the first term. And then for the second term, we're going to work our way up for the number inside the square root on that second piece here. So for instance, the next point here would be square root 3 over 2, comma, square root 1 over 2. Then the next point at pi over 4 would be square root 2 over 2, comma, square root 2 over 2. And then the point after that is going to be square root 1 over 2, comma, square root 3 over 2. And then finally, this last point is going to be square root 0 over 2, comma, square root 4 over 2. So kind of silly, might seem weird to, write these unsimplified. Square root 0, that's just 0. Square root 4, that's just 2. 2 divided by 2 is 1. But I think writing it like this, you can kind of see, it helps remember the value for these points, and then ultimately the value for sine and cosine. So if we look at the first coordinate for each of these, everything is being divided by 1/2. So everything is being divided by 2. And then it's square root 4, square root 3, square root 2, square root 1, and square root 0. Did it again. So we're just working our way down. Now for that second coordinate, we're working our way up. So we got square root 0, square root 1, square root 2, square root 3, square root 4. So they just kind of go in opposite directions. This one, the first coordinate is decreasing, the second, and then in the second coordinate, the square root term is increasing. So we're just kind of going around the circle, and these are the values that we get at these important angles. So when we look at one of these points, let's say for instance right here. Let's look at this point. What this is really telling us is that let's see here. Yeah, this one's really telling us that cosine of pi over 3 is equal to square root 1 over 2, which is just 1/2. And then it's telling us sine of pi over 3 is equal to square root 3 over 2. And that really doesn't simplify any further. So that's how we're interpreting these points. The first coordinate is the cosine value at pi over 3. The second coordinate is the sine value at pi over 3. And we know that because, why is the first coordinate cosine and why is the second coordinate sine? Well, from those formulas we just looked at. X is the cosine, y is the sine, and we're on the unit circle, so r is equal to 1. So x is equal to r cosine theta, y is equal to r sine theta, but we're talking about the unit circle here, so r is equal to 1. So really, on the unit circle, all of these points, the x-coordinate is telling us the cosine value at that angle, and the y-coordinate is telling us the sine value at that angle. All right, so this is going to be handy. So this is maybe a nice way to help remember what the cosine and sine values are at these important angles. So for the first coordinate, you start at square root 4 over 2, and then you just work your way down as you go around until you get to square root 0 over 2. And then for the second coordinate, you start with square root 0 over 2, and you just work your way up. And everything is just divided by 2 here. Now, what about tangent? It's also going to be helpful to remember tangent. So the first coordinate here is telling us cosine. The second one is telling us sine. What about tangent theta? Well, we can go through and we can calculate. So tangent theta is the y value divided by the x value. So for this first one, the y value is 0. The x value is 1, so we're going to get 0 here. And then for our pi over 6 angle here, and let's actually write in the angles. So tan of 0 is 0. Tan of pi over 6, what is it? It's y divided by x. So y is 1/2. X is square root 3 over 2. So we're going to get 1 over square root 3, or if we rationalize it, square root 3 over 3. Then tangent of pi over 4, square root 2 over, well, y over x. So square root 2 over 2 divided by square root 2 over 2, it's just going to be 1. So here, along this pi over 4, this is where y is equal to x. So that's why we get 1 here. And then for pi over 3, tangent of pi over 3 would be square root 3. And then tangent of pi over 2 is undefined, since the x value is 0 and y divided by x, y divided by 0 would be undefined. All right, so once you remember what these points are, or once you fill these in, you can then go on. If you don't remember what the tangent values are, you can go on and calculate those, because we know tangent is y divided by x. All right, so this is a way to kind of help remember what the trig values are at these important angles. We're going to be talking about these quite a bit, and it's probably easier if you just have them memorized or be able to quickly calculate them, rather than having to, while you're doing your work, go consult a calculator to look up these values. It's easier if you just have them memorized, because these are the angles we're going to be looking at the most. All right, so let's see how to use those to find any of the other important angles along our unit circle. So we were just looking at the first quadrant, but what about the second, the third, and the fourth quadrant? Well, there's going to be a few things to kind of keep in mind. So off to the side here, we're going to do a little sign chart based on the quadrants. And we're going to do a sign chart for sine, cosine, and tangent. So in the first quadrant, cosine, sine, and tangent. Cosine, again, is the x value, so all the x values are positive here. Sine is the y value. All of the y values are positive. So cosine and sine, for any angle that occurs inside this first quadrant, are going to be positive. And since tangent is sine over cosine, another way to think of it, tangent theta is also going to be positive. Now, what about the second quadrant over here? What are the signs for cosine, sine, and tangent? Are they positive, negative? Well, if we look in the second quadrant here, the x values are all negative. But the sine values, the y values, are still positive, still above the horizontal axis. So these are still positive. Tangent, sine over cosine. So we have a positive divided by a negative. It's negative. All right, what about the third quadrant down here? Let's do a sign chart. So here again, the x values are negative, and now the y values are negative as well. And tangent is sine over cosine, and we know negative divided by negative is positive. So down here, tangent is actually positive. And then finally, we have our fourth quadrant. Again, let's do a little sign chart. It's cosine, sine, and tangent. So down here, cosine, now we have this positive portion of our x-axis, but we have the negative portion of our y-axis. So that means cosine is positive, but sine is negative. And tangent is sine over cosine. So negative divided by a positive is negative. All right. So what this means is we can, if we know the value for these points in the first quadrant here, we can just figure out the points in all of these other quadrants by just negating, throwing in the negative where needed. So for instance, so how do we find other trig values? And it really comes down to just looking at similar triangles. All right, so for instance, let's say we wanted to find to evaluate sine and cosine at 7 pi over 6. So that's this ray right here. This is 7 pi over 6. How would we do it? So we want to know what cosine of 7 pi over 6 is. We want to know what sine of 7 pi over 6 is. And let me leave a little more room there. Well, we really want to identify the similar triangle. So let's form a triangle here. And we're really looking at this little triangle. And we want to find, which right triangle from the first quadrant would match up with this one. And that would be right here. And what are the coordinates of that point? Well, the first coordinate is square root 3 over 2. The second coordinate is square root 1 over 2. So what does that mean for our point down here? Well, let's just look. So this point right here is the length of this horizontal side here is the same as the length of this horizontal side here. The only difference is this one is to the left of the origin, so it's going to be negative. And same thing with the vertical distance here. The length of this side of the triangle is the same side as the length of this side of the triangle. The only difference is this one is below, so it's going to be negative as well. So the coordinates for this point are going to be exactly the same except negative. So it'll be negative square root 3 over 2, comma, negative square root 1 over 2. So that means cosine of 7 pi over 6 is negative square root 3 over 2. And sine is negative square root 1 over 2. All right, so we can play this game for other, for other points as well. So let's say we were interested in finding the coordinates for this point right here. We look for the kind of the similar triangle in the first quadrant. So let's draw in our triangle for this case. And where would we have a similar triangle? Well, that would be right here. And so we want to look at what are the coordinates for this point. So the coordinates for this point are square root 1 over 2, comma, square root 3 over 2. And if we're comparing these triangles, they both have the same height, and both of the heights are above, both of these vertical sides here are above the horizontal axis. Now, the horizontal sides here for the triangle, in the original one, it's to the right of the origin. In the one we're interested in, it's to the left of the origin. So that means it's going to be negative. So when we do this, the cosine value we know is going to be negative, and the sine value is positive. So the coordinates for this other point are negative square root 1 over 2, comma, square root 3 over 2. So the cosine value, we keep it the same, but we just make it negative. So we have our cosine value, we just make it negative. And then we have our sine value, and it just stays the same. It stays positive with what we had in the first quadrant. All right, so this is just a way to kind of help find trig values for points along the, along the unit circle for the rest of it. All right, one other thing to note here. Let's see. And graph's kind of full. Well, we'll yeah, I wanna mention tan. So when we look at this graph, and it helps to have it all pictured. And I might regret this, but let's get rid of these triangles. So I want to talk about tangent. So if we think of these lines here, let's get rid of the triangles. We're done with these. All right, so if we think about these lines that are going through the origin here, really what tangent is measuring is measuring the slope of these lines. So tangent theta is equal to the slope. So all of these lines go through the origin, so think y equals mx plus b. If they're going through the origin, then the b value, the y-intercept, is 0, so y is equal to mx. And if we solve for m, we get m is equal to y divided by x. So the slope is equal to the tangent. And if you think of the tangent theta as being the slope of all these lines, it might give you a way to help remember some of the tangent values. So for instance, if we're looking at the tangent value when we're on this horizontal line, so when theta is 0 or when theta is equal to pi, it's a horizontal line, so the slope is 0. So tangent of 0 is 0. Tangent of pi is 0. So the slope of this line is 0, and so the portion over here is when we have theta equal to 0, and then the portion over here is when we have theta equal to pi. So that means tangent of pi is 0 and tangent of 0 is 0. Now if we look on this line, this is the line where y is equal to x, so the slope is 1. And so tangent of pi over 4 is equal to 1. And that's because this ray right here is the pi over 4 ray. But then we also have that same thing down over here. and this one is pi over 4. So tangent of 5 pi over 4 is going to be 1 as well. And then we also have the other and if we look at this line also has that property where kind of y is very close to being equal to x. It's just the slope is negative. So y is equal to negative x on this line. And so that means the slope is negative 1. So tangent of 3 pi over 4 would be negative 1. And then tangent of 7 pi over 4 is going to be negative 1 as well. And then at pi over 2, the line is vertical. And at 3 pi over 2, the line is vertical. And vertical lines don't have an undefined slope. So we're undefined, tangent's undefined, and then tangent of 3 pi over 2 is undefined. So just a way to also help remember the values for tangent here. So if we remember the first quadrant, we can find all the values, the important values for sine and cosine. And then, once we find those, we can find tangent. But a few of these, it might be easier to think of the values for tangent in terms of just these slopes. So the horizontal line, slope is 0, tangent is 0. These lines where y is equal to x, that's where tangent is pi over 4 and it's just equal to 1. Or in the other direction, it's negative 1. And then when it's a vertical line, tangent is undefined because the slope is undefined. All right. So just some practice there, remembering how to evaluate trig functions. All right, let's actually let's get into it here. So all of that for this. So we're going to convert these 2 points from polar coordinates. So right now they're given in polar coordinates, and we're going to convert them into Cartesian coordinates. So let's start with that first point, 2 comma pi over 6. So what are we going to do? Well, we know x, well, we know r is equal to 2 and theta is equal to pi over 6. So what we're going to do is we're just going to plug those into our 2 equations. Just plug them in. So we get x is equal to 2 times cosine of pi over 6, and y is equal to 2 times sine of pi over 6. And that means if we evaluate cosine of pi over 6, we get 2 times the square root of 3 over 2. Evaluate sine of pi over 6, we get 2 times 1/2. And then simplifying, we get square root 3 and 1 for y. And then we just want to write this as a point. So the x coordinate is 3, the y coordinate is 1. So here's our polar coordinate representation for the point. Here's our Cartesian. All right, not too bad. What about this other point, 4 comma negative 5 pi over 3? Well, we know we need to evaluate sine and cosine at this angle, but first it might be easier to write this a little bit nicer. So we know that for polar coordinate representations, we can add or subtract 2 pi as much as we need to, and it really doesn't change where the point is. So adding 2 pi just takes us fully around the circle and we're back to where we started. So if we add 2 pi to this angle, it's going to change the representation, sure. It's going to give us a different version for the points, but it's still going to be the exact same point on the plane, just written differently. So we're just going to trace out the circle. We're going to go one full loop around, but we're back to where we started. So if we add 2 pi to theta, our radius isn't going to change, only the angle. So if we add 2 pi to this, we get pi over 3. And now pi over 3 is an angle that we can evaluate. Probably a little bit easier. All right, so let's go through the conversion here. So we know r is equal to 4. Theta is equal to pi over 3 in this more simplified version. We're going to plug them into our equations. So we get x is equal to 4 times cosine of pi over 3. Y is equal to 4 times sine of pi over 3. Let's do the evaluation. So pi over 3, cosine of pi over 3 is 1/2. And sine of pi over 3 is square root 3 over 2. Simplify. We end up with 2 and 2 times square root 3. And then we just want to put these back into Cartesian, make them into a point. So take the x value, take the y value, pair them up. And we get our Cartesian point as being 2, 2 square root 3. So again, here's our polar version. Here's our Cartesian version. So it comes down to just being able to evaluate those two equations. All right. Let's convert the other way. So let's say we're given a point that's given in Cartesian coordinates and we want to get it into polar coordinates. And this is where it's going to take a little bit more work. So let's look at this point. We know that x is equal to -2 and y is equal to -2. Just by looking at this point. This is given in Cartesian coordinates. The first value here is -2. The second value here is our y. All right, so let's use those equations. R squared is equal to x squared plus y squared, and tangent theta is equal to y over x. So when we actually plug in, we get -2 squared plus -2 squared, which ends up being +8. And then for tangent theta, we get -2 over -2, which is equal to 1. So this tells us tangent theta is equal to 1. And r squared is equal to 8. Now we can solve this equation. R squared is equal to 8. We can solve that, but we get 2 possible values for r. Do the square root of both sides, and we get r could be the positive square root of 8, or r could be the negative square root of 8. All right, so there's a little bit there. Here, let's write down what our equation is that we need to work with. So tangent theta is equal to 1. So we want to know, what angle when we plug it into tangent gives us 1. Let's go back to our little unit circle here. And we found the tangent values, the angle values, where tangent is 1. So we found those right here. Tangent of pi over 4 is equal to 1. But then we also found right down here, tangent of 5 pi over 4 is 1. So there's 2 on the unit circle here. There's potentially 2 values for theta. So theta could be either pi over 4, or theta could be 5 pi over 4. So when we do this, it looks like we have a few possibilities for r and a few possibilities for theta, and technically it's actually much worse than this. So not only do we have, looks like possibly 2 values for theta, technically all angles theta plus 2n pi. So if we add or subtract copies of 2 pi to either of these angles, go completely around the circle, we're back to where we started. Tangent at those angles is also going to be 1. So there's technically a whole bunch of angles, an infinite amount of them, where tangent, when evaluated, gives us 1. But to keep things nice, to keep things simple, we normally choose kind of our theta values to be between 0 and, 2 pi, just to keep it nice. Technically, there might be very few occasions where you want to pick a bigger angle or a negative angle. But for the most part, we'll keep them in between 0 and 2 pi. So we're only looking at pi over 4 and 5 pi over 4. But just be aware, potentially there's other ones out there. So we could add or subtract multiples of 2 pi and to either of these, and tangent would be equal to 1 at those angles. All right, so what do we have? We know x and y. We found possibilities for r and theta. Now we just have to, how do these match up? And to help us match things up, it helps to identify which quadrant -2, -2 is in. So let's get a really rough sketch here of the point. So let's draw in our axes. And -2, -2 means we go to the left 2 units and down 2 units. So we're down here. We're in the third quadrant. Maybe a little bit further down. Maybe right there. So it looks like here's the first quadrant, the second quadrant, the third quadrant, and then the fourth quadrant. Our point, -2, -2, is in the third quadrant. And so there's only one angle that falls, one of these angles falls in the third quadrant. So that's, if we choose that angle, and that's good, it's in the third quadrant, and we want to move into the third quadrant, so we're going to use the positive r value. So we have some flexibility here, but we just have to match them up correctly. So because angle theta 5 pi over 4 is in the third quadrant, we want the direction that we're going in to be positive, so that we go in actually that direction. So if we choose theta equal to 5 pi over 4, then we have to use the positive r value. So we have to use the positive r value there. If we choose the other theta value, well then we could do that. We could choose theta to be pi over 4. So 5 pi over 4 is good because that's in the correct direction here. But if we were to choose pi over 4, that's in the opposite direction. And so if pi over 4 is taking us in the opposite direction, we would have to use the negative r value to send us back. So pi over 4 is kind of capturing the correct direction, but it's the complete opposite. It's close, but it's the complete opposite direction. But we can adjust for the complete opposite by just negating the radius, the r value. So we have this direction sort of correct. We just need to completely reverse it and take us down to this point. So we could technically choose pi over 4, but then that would mean we have to use this one with the negative r value. So depending on which angle we use, that instructs us on which r value to use. So, as we've normally seen, there's lots of ways to represent a point in polar coordinates. So we have this point, -2, -2, given in Cartesian coordinates, and there's a few ways to represent this in polar coordinates. We could do either 5 pi or square root 8, comma 5 pi over 4. And this is probably the nicest one because the r value is positive and the theta value is between 0 and 2 pi. But we also could do the negative r value, negative square root 8, comma pi over 4. So both of these would be acceptable. So just various polar representations here. All right, so converting from Cartesian into polar coordinates takes a little bit more work because there's a little bit of, it's not a definitive answer, r is equal to this, theta is equal to this. We get a few choices here, and we have to pair them up correctly. And we really do that by judging, which quadrant is this thing in. That kind of helps us identify which angle to use. And then, if we're going in the right direction, we'll then just use the positive r value. If we're going in the complete opposite direction, like we were with pi over 4, it's okay, but then we have to use the negative r value. All right. So that'll do it for our introduction into polar coordinates. So last time we discussed, what the polar coordinate system. We introduced the idea of these important angles around the unit circle. This time we saw how to convert back and forth between Cartesian and polar coordinates, and we also had this nice kind of discussion about the unit circle and how to find the values of all the points and all the cosine and sine values around the unit circle. Or if we were kind of just going to the first quadrant here, really comes down to knowing these. And then we can figure out the rest of the points along the unit circle from these. All right, so that'll do it for today. Next time we're going to see how to kind of graph curves and regions in polar regions in the polar coordinate system. So we'll look at regions and curves. So we'll see that next time. Bye-bye.